sharing your screen now. You can go ahead.
Okay, and while he's doing that, I can give Torre a brief introduction. So we're privileged to have Torre Jorgenson provide the inaugural talk for the Permafrost collaboration team, which is highly fitting. Torre has a really rich history, not just in permafrost science, but also in terrestrial ecosystems in general, including everything from vegetation ecology, geomorphology, certainly permafrost, hydrology, and other topics. He's been working in Alaska since the I think even the late 70s, was a senior with ABR, Alaska Biological Research, for 24 years. Currently, he's the owner and founder of Alaska Ecoscience, which is a small business here in Fairbanks dedicated to similar types of research. And then perhaps especially notable for today, he was also awarded an honorary doctorate from the University of Alaska Fairbanks just this past weekend. And so we're all very pleased to be able to congratulate him now as Dr. Jorgenson. And with that, I think it looks like the slides are up and ready. And I'd like to turn it over to Torre.
Hey, good morning, everybody. Is the voice coming in fine?
Yeah, I hear you loud and clear.
Okay, thumbs up. Okay, so it's springtime in Alaska, and I'm really heartened to see a lot of friends on the screen, and want to provide an overview of the large amount of and dynamic research going on the permafrost and related to the global contribution of permafrost and permafrost carbon to the global system. So here I want to present this overview of the progress we've made in understanding responsive permafrost to climate change in Alaska. And I'm trying to get it to change the screen, and here we are. So here's an overview. I want to talk maybe about 5 minutes on each of those topics and provide a few highlights. I can't cover all the research that's ongoing, but provide a few examples of permafrost distribution mapping, ground temperature monitoring, active layer monitoring, studies of ground ice dynamics, a lot of work going on thermokarst patterns and processes, ecological relationships that control permafrost characteristics, and then a few words on soil carbon and greenhouse gas emissions and economic impacts. So about 25% of the northern hemisphere has some portion of permafrost in it. Here's our initial circumpolar map of permafrost led by Jerry Brown in 1997, showing these continuous, the discontinuous to sporadic and isolated permafrost zones. And permafrost is particularly fascinating for us permafrost researchers because it's a dynamic interaction of air temperatures, slope and aspect, soil properties, vegetation and snow at the boundary layer, and then disturbance, both from fires and humans. So in 2008, we made an improvement of the map for Alaska. Many of the collaborators are here for this talk. And we used a terrain unit approach based on a geomorphic map by Karlstrom. And we have a simple little model down at the bottom here where we relate the soil properties of different geomorphic units and then the temperatures at which they respond, and range from fully continuous permafrost at often -5 to -6 degrees. And then when we get up to the transition zones at 0 to -2, the coarser soils will tend to lose their permafrost faster than the fine-grained soils. And we have a large set of data of permafrost depths from coring and drilling across the state, all the way at 660 meters thick at Prudhoe Bay to just a few meters thick in the southern portion of Alaska. This map has been improved upon in terms of at least a spatial resolution of the distribution through thermal modeling with Vlad and his permafrost lab group. Here's a an example from Jacques Roth in 2012, where they did a higher resolution of permafrost distribution across the state. This type of mapping has the advantage of having a sophisticated thermal modeling component that can model temperatures at depth, but its weakness is that it has very simplified ecology in terms of trying to deal with the variability of ecosystems and soils across the state. And this map projects about 58% of the area being permafrost in 2010. Santosh Panda took this type of thermal modeling and applied it to a more detailed ecological mapping and set of soil properties from field studies, and used it to map the distribution of permafrost in the Wrangell St. Elias Park, as well as several other parks, national parks in the park system. Recently, Neil Pastic modeled permafrost distribution on using Landsat as a basis for spatial extrapolation. He compiled a seamless image of cloud-free Landsat images for across the state, linked those spectral characteristics to field observations at 16,000, almost 17,000 field observations, and then used a GIS layering approach of about 28 layers and a regression tree analysis approach to extrapolate from these data sets. And the advantage of this approach is that it incorporates a tremendous amount of variability of the landscape. The weakness of the approach is it's based on the field observations that often only go down to 1 meter. So this model is based on near surface permafrost at 1 meter and doesn't capture the permafrost that can be deeper than 1 meter. And particularly the weakness for here was mountain permafrost in rocky uplands where there's very little data and permafrost could be at 2 to 3 meters below the surface. This map came up with an estimate of permafrost as being 38% of the area when you include glaciers, but it does not include permafrost below 1 meter, and in particularly mountains. So this is an underestimate of the extent of permafrost in the state. For smaller regions, more detailed mapping can be acquired through the use of airborne electromagnetic imaging. And here's an example from Bert Minsley out on the Yukon Flats. And in fine-grained soils, particularly that have higher moisture content, it's in a very effective way at differentiating subsurface frozen conditions. And here at the top of the image, we have the imagery, Landsat imagery. Below that, we have a kind of a 3D cutaway. This was developed from multiple parallel flight lines and then extrapolating in between the flight lines. And then here we can see the subsurface distribution of permafrost, and you can see how complex this can be with talus underneath the lake and many open windows or zones in this discontinuous permafrost system. Recently, Misha Kineski and I upgraded the scale of this terrain unit approach for northern Alaska. And the advantage here is we're linking ground data to superficial geology, soil properties. Unfortunately, it's at a very coarse scale. Here's 1 to a million scale. One of the advantages of this approach is that we can link ground ice characteristics to these terrain units and estimate ground ice volumes, the type of ground ice, and the potential thaw settlement. Here, I'd like to highlight in particular these red zones that are particularly the Yedema belt along the lower foothills, and then these glacial deposits in the valleys of the Brooks Range. And these have potential thaw settlement capabilities of 3 to or 5 to 30 meters. And so tremendous potential for collapse of the ground surface if it thaws. Here's an example of updating of the thermal mapping by Sergei Marchenko and Vlad and his team as part of the integrated ecosystem model supported by the Landscape Conservation Cooperative. And this was extended from Alaska over into the Yukon region. And here are some estimates of ground temperatures when the GIPL model took the outputs of the coupled GCM and terrestrial ecosystem models. And here we have, by about 2100, the permafrost is almost completely absent from the boreal forest, central Alaska, but it still persists in northern Alaska. This is thermal model, has capabilities of estimating temperatures at tens of meters through the ground, but it doesn't capture the range of degradation that could occur. Here's a predictive model of where thawing is likely to occur. But even in this northern Alaska area, the response is dependent on ground ice, and you could have substantial degradation and still have at the surface and still maintain stable temperatures at depth. So another aspect of monitoring the health of and stability of permafrost is the ground temperature monitoring. Here's the entire GCM-TEM network. Here's summarized by Vlad after the International Polar Year efforts. And you can see that Alaska is contributing a large number of these monitoring sites through the efforts of Tom Osterkamp, Vlad Romanowski, Gary Clow, Frank Urban, and Kenji Yoshikawa. So we have a pretty good distribution of sites in Alaska, some nice transects in Canada, and there's a nice legacy of sites and some maintenance going on those sites in Russia. So here's an update that Vlad provided to me for his monitoring in northern and interior Alaska, so Arctic and Boreal. And this is an amazing data set, extending all the way back to 1977 and over a 20-year, or let's see, that's almost a 40-year data set, and shows the great benefits of personal commitment and federal support in maintaining a long-term data set. And northern Alaska, we see temperatures have increased just about 5 degrees or 3 degrees C at along the coastal fringe, and then inland and towards the foothills, it's been gone up by about 1 degree. And in the boreal forest, we have a record that extends back to the early 80s, and we see from that record that many of the sites have increased about 1 degree C. We had rapid warming in the 90s and early 2000s, a cooling period since about 2005, and then during the last recent few years, we've had a rapid increase in warming at the 15-meter depth. And also noticeable are these sites that are up near zero. They've gone almost isothermal, approaching the phase change, and get locked in at a relatively warm temperature, and will maintain that temperature over a long period as they go through a thawing phase change. We also have an incredible long-term data set from the Circumarctic active layer monitoring program going back 20 years to mid-1990s. And we have Kola Shikolamanov just sent me this slide. It represents the work of Fritz Nelson and his team over a long period. And these have a very gradual trend in increasing active layers. It's a pretty noisy system in terms of active layers fluctuating 15 to even 20 centimeters among years. But we have, during the last 10 years, we have this gradual increase again. And they have 11 sites on the coastal plain and another 13 sites in the foothills. But one of the complications for measuring thaw depths is that in extremely ice-rich soils, you can melt out the ice and consolidate the soils and have only a very small change in active layers. So a critical component to assessing the stability is measuring the surface elevations and subsidence of the surface. And here's an effort by Streletsky and his colleagues to monitor this subsidence of the surface up at Barrel. And they found a gradual decrease in elevations on the order of 10 to 15 centimeters over a 12-year period. Here's an example of permafrost or thaw depth monitoring that I've been doing on the YK Delta. It's a little bit different sampling system. It's more transect oriented and probing at every 1 meter. And in a discontinuous zone, these upper areas at 2.5 to 3 meters are these permafrost plateaus in a coastal setting. But as permafrost degrades, there are some additional monitoring challenges. I've got a better appreciation of really how complex active layer monitoring can be. A few of the issues here are, as the thaw settlement occurs, it alters the surface and water distribution. And over my 20 years of monitoring here, we have Thermokarst that's occurring not only at surface pits, but also along the margins. And then we also have old Thermokarst features of the old Thermokarst ponds, and those are starting to expand along the margins. But as we lose permafrost in the discontinuous zone, these active layer metrics become more complicated. And in this example, we have the active layer or the surface of the permafrost table here in these gray bars. And then we have these unfrozen zones. As far as the thaw probing goes down, often it's 1.3 meters to 2.5 meters. And I've highlighted these areas of unfrozen materials to probe depth in circles. And then, so in these areas, permafrost or the active layer can stay steady within the permafrost features, but then we get an increasing number of absent frost zones. And depending on how you calculate the metrics, you could show little change in the actual permafrost conditions above on these plateaus. And then we have the problem of multi-year or seasonal frost that can persist into the fall and across years. And in the discontinuous zone around Fairbanks in colder temperatures, we can often have the winter frost persist all the way into the fall, or the frost can persist for multiple years as a 20 or 30 centimeter layer of frost. And so then now we're having to detect not only the active layer, but the top of the frost, the bottom of the frost, the talics that develop. And it becomes, and another problem that we have is as the permafrost starts going through a phase transition, it just doesn't thaw right at the surface. It accumulates unfrozen water content, and the silty soils in particular become soft, and it becomes more difficult to encounter this hard active layer boundary, and it actually becomes a transition zone. So it gets complicated. Here's another approach to measuring thaw subsidence using inframetric synthetic aperture radar. And in particular, it was used to monitor subsidence after the Anaktuvuk river fire that burned in 2007. So it's a really powerful technique at looking at the seasonal subsidence after a fire. And over at the right, you can compare the post and pre images from the InSAR and see just the effects of itself, the spatial distribution of subsidence within the fire zone. It's a great technique for being able to map subsidence over large areas. The current downside for it is the relatively large footprint, pixel size of the imagery. Here's an example of combining resistivity and Lidar for looking at the distribution of permafrost and calyx on the Tanana Flats outside of Fairbanks. So we have our high resolution imagery, the Lidar-based elevations, and you can see the progression of collapse along the edges of these Thermokarst bogs. And then we have probing and coring to compare against the elevations, and then finally resistivity at the bottom here, showing the calyx developing tens of meters through the upper surface. And then at this site, particularly interesting is the development of a new permafrost mound that I'm presuming started from the cold period in the 1960s. So the boreal portion here can also have aggradation as well as collapse. An exciting new use of ERT by Tony Lekowitz is multiple repeating measurements. Here he's made a series of measurements, repeated measurements at multiple sites in the Yukon on a yearly basis from 2010. And here's an illustration of one site where the mean annual ground temperatures have stayed at 0 over the 6-year period. And he's been able to detect changes in resistivity that are presumably related to increases in unfrozen water content as the material starts going through the phase change transition. And here we have some thaw probing where permafrost was encountered within 120 centimeters. And then 6 years later, this probing has encountered frost much less frequently. So that's kind of mapping and determining the extent to distribution of permafrost. Now I'd like to talk some about ground ice characteristics, which are basically assessed from exposures and coring. And here's a couple pictures of our colleague Yuri Shur in the field and bringing the rich expertise of Russian knowledge to Alaska. Here are some pictures of the variety of ice that can be found in as segregated ice in soils, ranging from pore ice with the water and ice only within the pores of a sandy matrix to more complex structures of layered ice and reticulate and ataxitic. So at the ataxitic stage, the ice contents can be up in the 80 to 90% volume. And we can have pretty strong correlations of ice volumes by these different structures. And then there are various massive ice features. Here's an exposure of Yedema in the foothills Lutz Belt in northern Alaska. And this is a 30-meter tall exposure that is just about 80% ice. And this is a special type of permafrost developed during the Pleistocene when we had less accumulating over millennia. And both the wedges grow up with the accreting, accumulating surface and ice-rich ataxitic and other ice structures accumulating within the soils between the ice wedges. And there's several papers by Misha and his colleagues that have documented the characteristics of this. So I showed you a map earlier of this slush belt, and here's a nice profile of what it looks like with depth. But in many areas of Alaska and glacial deposits, we also have a legacy of buried glacial ice. Here's an example of deformed glacial ice at the Muldrow Glacier. This happens to be stagnant moraine material related to the Little Ice Age. But we also have abundant buried ice left over from the late glacial maximum, and there's even evidence of ice that persisted from earlier glaciation, so at hundreds of thousands of years. So in work with Misha Konevsky and his colleagues, we did a lot of sampling of exposures and coring along the Beaufort Sea coast and partitioned the variability of ice volumes by terrain units. And we can see that there is some large difference among some units. If you get to sandy soils, these Aeolian dunes, it's mostly right at the pore ice at saturation capacity. But many of these terrain units have volumes of ice that are up at the 80 to 90%, and it's this development of the ice-rich layer of upper permafrost. And the other thing that's notable is the real large standard deviations to these bars. There's a tremendous amount of variability, spatially across locally within a site. And then at the bottom, we have bars of estimates of the percentage of wedge ice. And often these terrain units have 10 to 20% of their volume in the upper 3 meters is due to ice wedges. Here's another interesting special type of ice that forms in old lacustrine basins. It's epigenetic ice formed during freeze down of previously unfrozen sediments. In a study with Michel for many years out on the Koyukuk Flats in Anoka, we studied these areas where the edema had degraded during the climatic optimum early Holocene, and then refroze 4,000 to 6,000 years ago, and now is undergoing another large degradation stage. And when the edema froze or degraded into these large lake basins and coalesced, when they froze back down, they formed these large bedded ice structures. And there's 3 to 5 meters of ice in these sediments. So Misha and Yuri and I took kind of information from a wealth of coring across both northern and central Alaska and developed some simple cartoons or concepts of how ice can be distributed in the top 10 meters. And here we have epigenetic ice formed during downward freezing of unfrozen sediments. And in ice poor rocky conditions, it can be a little bit at the top and very little accumulation with depth. Here's an example of freezing back down into fine-grained sediments like I just shown you in this lacustrine sediments. And here's the development of the ice ridge zone of the upper permafrost, this intermediate layer, and some examples of the size and distribution with depth of the wedges. We can contrast that with syngenetic ice. Here is an example of what ice would look like in its distribution in Yedema with extremely ice-rich contents in between the wedges going down to 20 meters, and these very large syngenetic ice wedges that can form 30 to 40, 50% of the volume of a profile. And here we have that same syngenetic ice and then the accumulation of this extremely ice-rich material in the intermediate layer. And around Fairbanks, our Yedema often responds to disturbance at the surface, and we'll have an ice pore zone down 3 to 4 meters after response to fire. The ice persists at depth where it's not, has not been degraded. And then with ecological succession and forest recovery, we get the accumulation of an ice-rich zone at the surface again. Because of this complexity of ice distribution across a landscape, I've worked with Misha to develop these conceptual models of the types of ice and the volumes of ice in relation to various cross-sectional profiles. So here's the cross-sectional profile concept for the coastal plain that has both the old coastal plain deposits and thaw lake basins and a variety of evolutionary stages within a lake basin. So one of the advantages of the terrain unit approach is you can start associating ice volumes with these different terrain units. And from our 2008 map, here's a recoding of the map in terms of ground ice volumes. And a couple of things that we want to, within the top 5 meters of permafrost. And a couple of things that we want to note here are these areas of extremely high volume ice content. They're primarily Yedema, and we have this less belt of lower foothills. We have substantial regions within the interior, particularly Seward Peninsula, the Koyukuk area. We have a large accumulation of Yedema surrounding the Yukon Flats, and then these during deglaciation and release of a lot of sediments, we also have irregular distribution of Yedema around interior Alaska. So if we take a prediction of LADS of losing this, or at least initiating the degradation of this material during the next century, these are the areas that are highly vulnerable to large-scale collapse on the order of 10 to 20 meters. But when permafrost degrades, it can degrade in a lot of different landforms depending on ice contents, its distribution and type of ice. Here's just a screen overview of the wide ranges of morphologies of how the terrain can respond, all the way from glaciated glacial thermokarst and glacial deposits to thermokarst bogs and fens in the interior to ice wedge degradation and related thermal erosion gullies on the north slope and thaw slumps. What I want to do now is just highlight some progress or research into analyzing and evaluating the kind of the patterns and processes of a few of these thermokarst terrains. So out in the Seward Peninsula, we have this extremely ice-rich silt Yedema. Here's a lake that's progressively thawing into this Yedema mound. And in this example, we have 24 meters of collapse from the surface down to the bottom of the lake. Ben Jones has done a nice analysis of the transformation of this landscape through using satellite imagery and historical area photography, and this map both the land gain from the drainage of lakes in green, and then the land loss from lake expansion thawing around the margins. And from his analysis, the number of water bodies increased 10.7% during this 57-year period or approximate period. But then the total surface area decreased almost 15% from this Thermokarst lake drainage problem. So Dave Swanson worked for the Park Service, has an elaborate permafrost monitoring network within the Arctic network of parks, and he has mapped retrogressive thaw slumps within these parks doing a manual interpretation of high resolution ICONOS imagery. just browsing, roaming and browsing the imagery. And he's mapped out 724 of these retrogressive thaw slumps. Many of them are associated with glacial deposits, presumably with buried glacial ice. And these thaw slumps have now exposed, or at that period, 2.84 kilometers of bare soil. He's also been monitoring these features with photogrammetry, with structured for motion. He's now migrated over to structure for motion imagery with Matt Nolan. And here's an example of an orthomosaic draped over the DEM, and also a mapping of almost annual retreat of a couple of these features. He's got dozens of these that he's monitoring on a 2 to 3 year basis, or a few of them even on an annual basis. So Balzer took a set of his own mapping, Andrew, and the mapping done by Dave, and evaluated the terrain characteristics and developed a modeling approach, regression tree modeling with many different terrain components, and came up with a kind of predictive model of where the terrain types are that are going to be at highest risk for both detachment slides and regressive thaw slumps in the Brook Range and foothill. And you can see that there's some peculiar distribution to these active layer detachment slides in terms of its relation to geology, and similarly, these retrogressive thaw slumps more constrained to these glacial deposits in the valleys. Ice wedges are another type of ice that's prone or susceptible to degradation. And here's a time series of photos that I compiled for Prudhoe Bay going back to 1949. And for here we have, because it's within the oil field, proximal to the oil field, we have a nice compilation of imagery for a site. And here we can see very little degradation in the going up to 82, and then one last image from 1988, and then after that we see pretty dramatic development of thermokarst pits and troughs within this landscape. And if you could look at the initiation or progress of degradation over time, we had a big change from the late 80s, onset in the 90s and 2000s, and in this case, I attribute it to a particularly warm and wet year in both in 89 and 1998. So initially kicked off in 89 and then reinforced by another extremely warm, outlying warm event in 98. So Anna's expanded this evaluation to on a circumpolar wide, and documented the onset of degradation at many sites across Alaska, Canada, and Russia. And here's an example from Janet Jorgenson and her monitoring in the Arctic Refuge going back to 88, and a nice photo series of the onset of this ice wedge degradation. Here's an example of collapsed scar bogs that's prominent in the interior, and this is out in the Inoko Refuge. And we have a variety of sphagnums with different colors that provides a nice color coding to ages. And this bright green are areas with sphagnum riparium that have degraded in the last 20 to 30 years. And some of these older brown areas with another type of sphagnum, they can be as much as 300 to 500 years old. But in this area, almost 90% of the permafrost has already collapsed within the last 500 years. So it's not just a new process, but it's responded to smaller climate changes over time. And then on the Tanana Flats, one of kind of a ground zero for permafrost degradation in the interior, and here's a nice example of forests, birch forests collapsing into the fens. And this has mostly been going on during the last 50 years. Much of this area kind of refroze during the Little Ice Age and is now undergoing another episode of collapse. And Mark Laura did a nice remote sensing analysis of the loss of birch forest and the increase in wetland area within this period through a remote sensing analysis. The information of the patterns and processes from many of these local studies has been taken by McGuire and his crew, in particular Helen Genet, in developing a model of the predisposition of various landscapes across Alaska and their potential for collapse or disturbance. And this Alaska Thermokarst model is linked to an integrated ecosystem model to assess the effects of thermokarst both on ecosystem structure and function. But the aggradation and degradation of permafrost is a complex interaction between geology, climate, microclimate, vegetation, as it perks down through the surface properties, interacts with the soils and the soil properties, and ultimately leads to adjustment of the active layer, and then interacts with ground lice and can lead to slope failure and thaw settlement. These can lead to positive feedbacks with water accumulating on the surface, and as soon as you disturb the surface, just about everything about the system changes, and that can lead to nutrient changes and then vegetation feedbacks. So it leads to a complex interaction of all the ecological components in developing a new and radical type of system. Working with Vlad, we assessed the effects of succession on soil temperatures, going all the way from a barren silt to a forested system to tussock bogs, kind of the oldest wetlands in our interior system. And ground temperatures here can vary almost 7 degrees across this ecological succession. So very strong feedbacks from vegetation, snow, and soils and mosses at the surface. And then once you start having some collapse and impoundment, you can increase water temperatures or ground temperatures underneath the water by almost 11 degrees over time. So you have a total variation of soil temperatures across the boreal landscape of 10 to 12 degrees centigrade. Because these temperature variations from ecosystem properties, these are nearly twice as large as the projected climate warming. So it makes it a very large and difficult factor into trying to assess what the responses of permafrost will be when you have these large ecological factors. So these feedbacks, both from water and vegetation, allow permafrost to degrade in cold regions in Alaska at minus 11 degrees C, even with Daniel Fortier's work up in the Canadian Arctic, even extensive degradation going on at minus 16 degrees C. And yet we have permafrost that can persist at temperatures at up to minus 2 degrees above C in the King Salmon area. And here's a picture of this ice within these glacial Lacustrine deposits. So not only do we have the complexity of ecological properties, but we have the landscape topography and geology to deal with. And we've tried to partition this variability into 4 very simple landscapes: rocky uplands, silty uplands with Yetama, to the sandy lowland types of the Yukon flats with sandy materials at depth that are highly porous when you lose the permafrost. And then these peat silty lowlands that have very low conductivity silts when they thaw, and a high preponderance of evolving to stagnant bogs. So Yuri's developed kind of a way to categorize these permafrost responses in terms of both ecosystems and climate. So we have a gradient of early to late ecosystems, and then we have a gradient of climate going from very cold to unfavorable. And you could have a climate-driven system where permafrost forms at early succession under cold climates, and as the climate warms, or you go to late succession, you can have the permafrost characterized as climate-driven to ecosystem-driven to ecosystem-protected, and I showed you an example of this ecosystem-protected permafrost down at King Salmon. Here's a picture of ecological succession floodplain evolution up on the Colville Delta, where we go from almost no ice during the original point bar stage, and through the accumulation of ice, segregated ice in time, and ice wedge development, we accumulate 2 to 3 meters of ice in the landscape, and that can feed back to flooding processes where this has raised the abandoned floodplain almost 2 meters above the early point bar successional stage, and that greatly reduces the flooding and leads it to thick organic accumulations. But after 2,000 to 4,000 years, it becomes so ice rich that it leads to instability and the development of these Thermokarst lakes. So there's an intimate interaction between the ecosystem successional evolution to its susceptibility to degradation at the end. But we also have recent permafrost degradation in the boreal zone around Fairbanks, where temperatures, mean annual temperature was around -3. Here's an example of new permafrost formation and heave that I observed in 2004. And then at a repeat monitoring site, here's a new frost mound that was not present when I initially put in the transect in 2005, and this recently developed. I'm presuming it was happened during the very low and low snow years, 2005 and 2000 to 2010, and heaved up in that period. So quite sensitive to temperature and ecological conditions. So getting to kind of the last factors here is fire. The predictions are for more frequent and more severe fires with a warming temperature. And here's a very innovative approach that Ben Jones has used to monitor the subsidence or response of permafrost to a fire up on the North Slope, the Anaktuvuk River fire in 2007, and used repeat Lidar to look at the degradation of these ice wedges through this time series of Lidar. So Lidar is a particularly powerful tool for assessing surface deformation. The resolution of it and accuracy of it is terrific, but the costs of it make it limited to smaller and regional studies. And then we have the boreal fire in the boreal forest. Here's an example of a fire from 2010 on the Tanana Flats, and it's the first time that I've seen a fire degrade the surface so that it's collapsed down below the water surface. So a radical transformation from forest that was about 2 meters above these Thermokarst bogs, and now it's collapsed and inundated by water. So Dana Brown, working with Vlad, kind of looked at the interaction of fire severity and changes in climate over time. And in this area, if you have fairly moderately severe fires, reducing the active layer down or organic layer thickness to 7 centimeters, you can have an onset of degradation with climate warming since the 80s. But then here is this permafrost regrading at the surface in response to these colder temperatures in the mid-2000s. But if you go to completely burning the organic layer off, permafrost degrade very quickly early in the century, had some reaggradation during the 60s, and then re-degraded again in the last several decades. But what this is pointing out is we're entering an era where fires will pretty much eliminate permafrost and not be able to recover with the onset of warming temperatures. I showed an example of how forest succession could lead to re-aggradation of permafrost, and Misha and I did some coring of or jackhammering of pits in black spruce areas and ran into this nice example of permafrost that's grading up into the root zone and led to forest death and dieback of black spruce, and they're trying to put up new advantageous roots as the permafrost is degrading up around its root system. So a couple last slides on implications. One is the large effort by the permafrost carbon community. I'm not going to get into much on soil carbon other than there's been a new inventory of reporting of the permafrost carbon pool across the permafrost region, leading to 1,000 petagrams. And this permafrost thaw is likely to accelerate the microbial breakdown of organic carbon and release of greenhouse gases. But the magnitude and timing of this gas emission from these regions and impact of climate change remains uncertain because the complex interactions of how the ecosystems transform to this degradation stage. So a number of large team of authors and collaborators working with Ted Schur to try to assess this permafrost carbon feedback. And then McGuire and colleagues have come up with an assessment of the ecosystem carbon balance of Alaska during the next century and identify these pathways of gains and losses. And we have this very large input from net productivity, and then that's trying to balance out the respiration decomposition of this carbon. So large exchanges, and then we have some fairly unknown levels of carbon or methane emissions from these bogs and fens and lakes that Katie's working on with these inland surface waters, and these can be substantial. So this analysis is expecting a large increase in net primary productivity, and that will balance out these losses from respiration and emissions. So this is leading to still substantial uncertainty of whether Alaska is going to be a net sink or source for greenhouse gases. And since I've touched on this in such a brief way, I'll rely on you to go to the vast literature on this permafrost carbon feedback. And finally, the estimated costs of permafrost-related damages are substantial. Here's a recent paper by Melvin and colleagues estimating what the costs are in millions of dollars. And they're projecting potentially trillions of dollars of damage and mitigative work, primarily to buildings and airports, but also to roads, pipelines, and railroads. And here's an example of the costs of adapting to a changing permafrost environment. This is our local road out in Goldstream, and they're redoing the road with 4 inches of foam insulation, an extremely expensive proposition of trying to stabilize this road in a Yedema deposit. So there we are. That's a brief overview of a tremendous amount of research that's going on in permafrost-related studies. So we've made tremendous progress, but then we have a big but. And the complications are we have this tremendous, beautiful climate gradient across Alaska. It creates a wide range of permafrost temperatures, ground ice properties, and ecological conditions. So to try to integrate, evaluate, and assess that over a large area is a tremendous challenge. Currently, a variety of different mapping approaches indicates that 50 to 60% of Alaska has permafrost, but our capability to track these overall changes over time is poor. We're still challenged to provide an accurate assessment of permafrost and how it could change, or be able to measure that change over 5 to 10 year periods. We found out that ground ice, its morphology and volume is the response to temperature, soil texture, and ecology, but it is one of our least understood permafrost properties and is only very crudely mapped. So it's a huge data gap that we need to address. And then mountain permafrost and rocky uplands, these are poorly understood. They're hard to drill in. The resistivity doesn't work very well. It's hard to get a temperature probe in the rocks, and there's almost no data coming from mountain permafrost in Alaska, but that's in a very extensive portion of our terrain. And then we've been finding that permafrost can be highly resilient to vegetation and soil development. I showed you an illustration of Yedam being able to respond to persist after fire disturbances. And yet permafrost can be highly vulnerable due to water, and these ecosystem interactions greatly complicate our projections of response to climate change. And we've been finding permafrost degradation occurs in many forms. Some types of permafrost are well documented regionally, and Thermokarst lakes in particular, but our overall knowledge of Thermokarst landforms across the state are poorly documented. Then we've made substantial progress in understanding the effects of permafrost degradation on carbon balance, but there's still uncertainty whether Alaska will be a net sink of source for carbon. And then finally, economic costs of permafrost degradation are expected to be staggering. And we have little political will to address the huge vulnerability we have in responding to infrastructure damage and repair. So thanks a lot. I'll take questions.
Great, thanks a bunch, Torre. That was a fantastic overview. And we've run a little bit over, but we still want to leave time for at least a couple of questions. And also, I think it's worth pointing out that as the talk was going on, people were using the chat window to contribute some links and other bits of information that relate to this, which is really great. And hopefully, amongst us with IARPC, we can find a way to capture that as well and make that part of the online recording of this this webinar. So are there any questions for Torre?
Andrew, this is Jessica, and I just wanted to point out that we have another meeting starting in 20 minutes, so that's the hard stop on this meeting, okay?
Okay, good to know. Thanks, Jessica.
This is James Fortain out in Alaska. I am the NOAA Regional Climate Services Director for the Alaska region. And I uploaded just a bit ago to the team through chat an article that came out today on the sort of devastating impacts of permafrost thaw in Alaska right now being experienced by native communities that rely on underground ice cellars to store their winter or their summer catches of whale and caribou and all that. They can no longer use, in many places, they can no longer use those ice cellars as they are degrading to the point of disuse. And so it's a tremendous challenge. And Torre, I appreciate you bringing up the economic impacts, but this is one of those sort of non-economic but devastating service impacts related to climate change, and especially its role in permafrost thawing. So I just wanted to share that. That's kind of my specialty. I'm not really the science guy, but I'm the service guy. I try to hold the hands of the researchers in the research community and also the service folks and the decision makers in Alaska. And that's, I really appreciate this kind of research going on because it does enable decision making in Alaska for the kind of thing I uploaded there. So thanks for letting me listen in and to share that with you all.
So I didn't have a chance to villages that are currently highly threatened from permafrost degradation. For example, Kotlik, Nutok, Shishmaref. The foundation for those villages is going to be gone in 30 to 50 years. Their village is not going to exist anymore in 30 to 50 years. And it's going to cost 100 million, maybe 200 million to move a village. And right now, everybody is at the agency levels are ducking that issue. FEMA didn't want to have to pay for the moving of Shishmaref or Kotlik, and the state doesn't want to do it, the feds don't want to do it, and it's an impending urgent transformation that's going to happen here within decades.
If I could just share briefly in response, Torre, one of the issues is that many of the villages do not want to move or want to move to a place that in 30 years is still going to be in harm's way. And that's a result of their relying upon subsistence to keep them alive. And when you move them from the coast, where they have this rich access to subsistence hunting, and move them 30 miles inland, so they'll be out of harm's way, you've got a problem that's both cultural and subsistence that is generated for those villages. What are they going to hunt for food? How far do they have to travel to get to their hunting grounds, both inland with caribou and moose and whatnot, and then ocean marine mammal base. So it is a very challenging set of problems, both for the communities to come to realization of whether or not they can move. And then, of course, as you mentioned, the economic disability of the country right now to either be motivated to do that or actually fund it as well. So it's a challenging set of problems on both sides.
Very well said. Thank you.
Torre, short question, Torre. Any chance to downscale this the excess ice content maps from terrain unit to ecotype?
Presumably, and ecotypes would be a good way to go. So for these regional maps, particularly the Park Service, we have some pretty good data that we could kind of downscale to this ecotype map basis. One of the data gaps kind of statewide is a new superficial geology map at a sufficient resolution, and we're kind of stuck with this 1960s Karlstrom map, and we're in an urgent need to improve and increase the resolution of that so we can relate these ground ice to geomorphic units, and then we could start incorporating that into thermal modeling of LADs to increase the predictive capability of how permafrost will respond. But ecotypes would be a good intermediate step.
Great, thank you.
Well, because we're kind of short on time, I think we're going to probably try and cut off the questions here. But thanks again, Torre. And your last point actually is one I think a lot of us would echo too. Superficial geology is just a critical data layer, and it's something that statewide we don't have a very detailed data set of. In deference to the next meeting coming on, I think we're going to wrap it up pretty quickly here. If anyone has any super critical